Day 3 instruction, they're going to provide us two different sets here. By the way, I want to introduce the terms one-to-one. If I told you that this is function f and this is function g, just a side note, we could test to see if something is one-to-one. One-to-one means that every x belongs to one specific y, and it's special. So like -6 belongs to 2, and no other x value belongs to 2. -3 belongs to 5, and no other x value belongs to 5, okay? So exactly one x belongs to one specific unique y value. So what it would not be like is -6 goes to 2, -3 goes to 2. That could still be a function, but it's not a specific type of function called one-to-one. So this is in fact one-to-one because nothing repeats itself. It is a function because I have input and output values. And remember, to be a function, it means that every x value or input value is going to map onto a maximum of one y value. Now that y value can repeat in order to be a function, but it wouldn't be considered a one-to-one function. So this is not only a function, it's one-to-one. Is this a function? Is g of x a function? Does it have input and output values? Okay, and I can quickly tell if it's a function if I look at the x values and they never repeat. Good, it's a function. Is it considered one-to-one? It is. Now, this is the way that this particular book writes this. I would like you underneath this to write it like this. We're going to do a composition of functions. Please write it like this. These are two unique ways to illustrate the same mathematical language. So how does this work? We are going to start with the x values of the inside, or the second function. So that's what we're going to do first of all. To get this answer, I'm going to start with the x values, always the inside or the last one. Okay, it's x value. So I go to -6 and I draw an arrow. The output to -6 is 2. Then I drop into the second function and I see, is there any positive 2's in the second function, which happens to be g. Oh, there's a positive 2. So there's the positive 2, and the output is 0. So -6, 0 now belongs to this function, this composition of functions. Okay, let's try this one. Okay, so I start with the inside and I start with the x value. So -3 maps onto 5. Okay, so I have 5. Now I'm going to take that output value and I'm going to apply it to the outside function g. And it doesn't always mean there's going to be one. In this particular set, is there a 5? Oh, there's a 5. And 5 maps onto 11. So I plugged in -3, and the output of this composition was 11. It's not always going to be able to find a second set in function g. Okay, so 7 maps onto 4. Can you see here how we have no output value? So output value is 4, but we have no input value in the second function of 4. So what do? We just don't write it down. Okay, let's do the next one. 8 maps onto 1, and there is an input value of 1 that maps onto -3. So this is 8, -3. Okay, that's the first part. Now the second part, if it's possible, can we evaluate this? So I'm going to do f. Now this is one way to write it. It's not how I would choose to write it. For myself, I choose to write it like this. They mean the exact same thing. So if this happens to be part of the test, which is your written part, that is not multiple choice, you could write it either way. They are both equivalent. So for me, it makes more sense. It says, okay, I'm going to plug -3 as an input value into g, and let's see what I get. Okay, ready? Let's go up here. Bless you. So I find -3 in g. Oh, sorry. Do you see how I actually, remember how I switched them, by the way, before I started filming? I meant to switch them over here. My fault. For those that are re-watching this, I switched it. You can see my sloppy writing before I started. So let me start again. This is equivalent to this form right here. Okay, so what does this mean? I start on the inside with the input value of -3. So I'm going to go to function f. Okay, here's function f, and I find -3. Okay, got it. Here's -3. It has an output value of 5. So now I'm going to rewrite this with 5. I replace this with the output, which is 5. And now I'm going to go to function g, and let's find, is there an input value of 5 in function g? There is, and the answer is 11, and that's how we write it. So this particular answer is equal to 11. Check with your partner to make sure you understand. let's look at another example. Remember that this is just another form of the exact same thing. So when I come up with this set, if I would have enough room, this is equal to, okay, here we go. I'm going to start on the inside. I'm going to find the input of G. So 1 maps onto 5, and now I go to the outside. Now I take 5 up to the top. Oh, 5 maps onto 8. So 1, 2, 8. Can you raise your hands if you had 1, 8? 2 people. Okay, let me slow up here. I start on the inside. I start on the inside with the input. 1 maps onto 5, and now I go to the second function on the outside. 5 maps onto 8. Let's go to the next one. 2 maps onto -7. Oh, here's a -7. -7 from the input maps onto 0. So 2 goes with 0. Let's try 3. 3 goes to 4, and 4 goes to 9. So 3 has to go with 9. And let's try 5. 5 maps onto 10. Is there any 10s up here? There's no 10 for the input, so I just don't include it. So this is what I have. This is what I have right now. This is my function. By the way, is this one-to-one? Is this function one-to-one? And how would you explain that? I know it's one-to-one because every f maps onto a unique y. Okay, let's mix it up now. Here's our next one. Let me grab my paper. Please write this down for example number 3. Example number 3. Same concept, so I do want to rewrite this. It's just my preference. I do want to rewrite this. This is what I'm doing. I'm going to take G, and I'm going to plug it into F. Okay, so I'm going to take G, and I'm going to plug it into F wherever I see an X. So I'm writing down F, but in the place of the variable X, I need to place X squared minus 5. Now, when I simplify things, the -5 and the +5 are additive inverses. They're going to disappear, and I'm left with the square root of X squared. Now, what happens to the square root and the square? Yeah, they cancel out, and I'm just left with X. And now I'm able to substitute in the 3 for the X. So when I substitute in, I get an answer of 3. So this answer is, in fact, just 3. Okay, let's do another one here. Another one here. Is this an example of a function? Turn to your group of 2, your group of 4. Is this an example of a function? Yes or no? And what is your reasoning? Is this an example of a function? To be a function, you have to have an input and an output. This is just a set of numbers they called f. Now, let me change this up. So I have 5, 3, 2, 0, 3, 0, and 5, 2. Is this now a function? Okay, why not? Explain to your partner. Why is it not a function? The first thing I do is I look at the x's. If they ever repeat themselves, which they do right here, they have to be mapped onto the same number. This is not. Okay, let's change this up. Is this now a function? It is a function. We have 1x that maps onto a maximum of 1y. Okay, we're good. Is it considered a one-to-one function? Turn to your partner. Why is it not considered one-to-one? Okay, I'm going to give you a graph right now. Please write down, let's go with, we're going to call this function f, and let's say function f looks like this. So it's comprised of ordered pairs, x and y, such that y is equal to 2x plus 1. Now, for those that maybe missed class or looking at this and they're like, what does this mean? All this means is when we look at this, equation, I want to know, is it a function and is it one-to-one? I'm going to press pause on this. I want you to turn to your partner. I'm going to give you about 45 seconds to get an answer and justify. How would I maybe go about doing this? Because it's a linear function, I can easily graph that. You learned this in 8th and 9th grade. I'm going to start at +1. And from there, I'm going to use the slope to create the line. Up 2 over 1, up 2 over 1. And this is what my line looks like. And this proves to me that every x maps onto one and only one y value. That makes it a function. Not only that, I can see that we have a pattern here on the slope, and that every y value that corresponds to an x is unique and different from a different x value. So another way is, I guess I could create this, and I could do, for instance, 0 maps onto 1, and I could do 1 maps onto 3, and 2, you could keep going, right? And you can see this pattern of what's created, that every y value is unique to an x. Okay, next up, let's talk about really quickly, how do we find inverses? Again, you learned this freshman year. Let's start with this very first one. Now, there's different ways that we can find an inverse. Let's start off with this particular problem, 2x minus 1. How do we find the inverse of this? Well, really quick, by the way, let me go through this first of all. Let me just do this. I can show you this part. If this is function y, and you were asked to come up with ordered pairs, make sure you don't have a phone out or earbuds in. If you were asked to come up with ordered pairs of its inverse, all you're going to do is you're going to flip the x and y's, or flip the domain and range. What is the domain of the original function becomes the range of its inverse. What is the range of the original becomes the domain. And in doing so, when you graph it, so if I graph this, and then now I'm going to take a different color, and I'm going to graph the inverse. So here we go. 1, 0, 3, 1, 5, 2, 7, 3. And if I graph this, what I would see, and hopefully you remember doing this with Ms. Castro or whoever your awesome teacher was for algebra, if you remember this, they would tell you that we could fold along the line y equals x, and these points would map directly onto each other. So if I gave you this and I said, okay, fold along this line y equals x every single time. Sometimes we have to limit the domain based on the function, but every single time they will fold onto one another. Do you remember doing that? Slightly? Okay, let's take a look at this particular problem. So how do we find the inverse? Algebraically, we can switch the x and y. So this is the same as y. So switch the x and y. Easy enough. And then we can really quickly solve here. So I'm going to add 1 to both sides. X plus 1 equals 2y. Divide by 2. And I'm going to rewrite this right now. This really wasn't y, it was f of x. So it doesn't matter if it goes on the left or on the right. But how do we denote it being an inverse? We're going to have that little negative 1 up there. So if I graph these two functions, I can promise you that they are going to reflect across the line y equals x. Good with that? Do you remember in algebra how to prove algebraically their inverses of one another? Yes, no? Do you remember this? Okay, everybody write this down. This is a concept from Algebra 1-2, but it's very possible that you forgot it. We need to do this, and we need to do this to prove. I'm going to do the first one. You only have to watch. You're going to do the second one. So this is the one I'm going to do right now. You have to do it both ways, and you're going to see every single time we get the exact same answer if these are inverses of one another. What the heck does this mean? I personally don't like that writing. I like it get written like this. So I'm going to take this, and this means I'm going to write down function f. Okay, here is function f. Okay, 2, but I'm not going to put an x, minus 1. Write down the outside, but where you see the variable, which is x, I'm going to replace it with the inverse. Okay, what is the inverse? It is x plus 1 over 2. What happens to the 2's? I got a 2 on the outside and 2 on the bottom. What happens? They're reduced down to 1, right? 2 divided by 2, so I have x plus 1 minus 1. These are additive inverses, and I'm left with simply x. Every single time, if you did it correctly, you're going to end up with x. Now to prove, and it's very possible you're going to have to do this for your test, to prove that they are inverses of one another, you have to do it both ways. Are you ready? You're going to be timed right now. I want you to do it this way. I'm going to give you a 10-second head start. I want you to do this one. I'm going to start writing it just in case you prefer this denoted this way. Ready, get set, go. 30 seconds. I wrote down the inverse, and then where there was an x in the inverse, I put a big parenthesis. And inside of there is where I put the function, 2x minus 1. Okay, here we go. Additive inverse is -1 and +1. And then I'm left with 2x over 2. The 2's are going to be reduced, and I'm left with the inverse of f of x equals x. I just proved you have to show both ways. You must show both ways. It's very, very, very high percentage that you will have to do this on a test. Okay, are you ready? Here's your next one. Let's try one more. Our first step is going to be, can we just come up and find the inverse? So please write down g of x is equal to x minus 2 to the third. How do we find the inverse? Well, I'm going to be lazy. I know this is the same as y. I'm going to switch the x and y. And now I'm going to isolate the y. So how do I remove a cube? We have different ways that we can do it. I'm going to do the cube root. So I'm going to do the cube root on both sides. In doing so, the cube root and the cube are going to simplify. You may think of them as canceling out in your mind, but they simplify to 1. And I have y subtract 2 equals the cube root of x. Now to isolate the y, I'm going to add 2 to the opposite side. And this is the inverse. So this is what g of x is, and the inverse of g is equal to the cube root of x plus 2. Okay, taking this like a quiz, I'm going to press pause. Please do the same if you're rewatching this. I want you to prove that these are inverses by doing the following. So you're going to do g inverse of x, and then you're going to do it the opposite way. I'm going to walk around. Let's see if you can have this done. Let's give you 2 minutes. Ready? Get set and go. Feel free to work a I can start by doing this. I know people in class are working on this as well. This is the same as x to the 1/3. These are the exact same. This is written radically. This is written in rational exponent form. Either way, you simplify to 1, and I'm left with x. Do this the second time. You have to do it both times. One time is not enough. Now the second time, I'm going to have the inverse on the outside. That means that I'm going to start by writing down the inverse. So this is the inverse. And then I'm going to leave a blank spot wherever the variable was, which is inside of this radical. And I'm going to replace that with what g of x is, which is x minus 2 to the third. Now, if you prefer to write this as a rational exponent, a cube root is the same as to the 1/3. So when I'm writing this down, I have x minus 2 cubed. These are going to be, in your mind, you may think canceling out, but they're reduced to 1, and then I have x minus 2 plus 2. And there we go. I've just proved algebraically that they are inverses of one another. I'm going to write down the inverse of g of x. I'm going to take the inputs and the outputs, and I'm going to switch the order. So 3, 1, 7, 5, 11, 9, and 15, 13. This was a function. In fact, it's a 1-to-1 function. This is also a function and a 1. Please look at your packet. I'm going to go over what is going to be the required work here. We're going to do one more composition of functions. I see one more type of problem. Composition of functions is something taught in Algebra 3-4. It's at the end of Algebra 3-4, and you guys never got Algebra 3-4, right? We're going over the past it. So if you are in my specialty advisory class, like Mara, like Gabe, you may have seen more of these than other students. Here's the first one. I want us to do this together. I want us to do f of g, and we are going to evaluate it for 4. Okay, now I know we've done something like this, but let's have you do this again. Let's say f of x is equal to 3x plus 2, and g of x is equal to x squared. Okay, ready? I want you to do this one problem, and then I'll go over what is your assigned homework for this weekend. So I'm going to take function g and I'm going to plug it in to f. Thumbs up, thumbs down if you got this answer when you're done. For those that are watching the video, you should have had through number 25 done. I want you to do, real quick, this video covers 26 in the packet that is titled, Basic Function Concepts. I would like you to do 26 through, give me a second, 26 through through 49. 26 through 49. I'd like you to do those problems. Now, there's going to be a very short secondary video that talks about even and odd functions or neither functions, along with going back over inverse functions, and that will cover problems 50 through 58. Please hold on here, please. Attention up here. There's going to be one more instructional video that's going to say day 4. That's going to be released this weekend. Your responsibility is to have 26 through 58 done, but you cannot do this portion until you watch the new video that will come out. Where will you find it? It will be within the playlist of this basic function concepts.